Thermodynamics is the study of energy conversion between heat and mechanical work, and subsequently the macroscopic variables such as temperature, volume, and pressure. In this module we will discuss the second law of thermodynamics. The second law of thermodynamics describes the natural heat flow of any system, which is always from high temperature Th to low temperature Tc. Here the ice melts to water and it moves from order to disorder of molecules in its structure as shown in the figure. Here the spontaneous flow of the system moves towards an increase in its entropy. Nicolas Leonard Sadi Carnot, French physicist, who is considered to be the father of thermodynamics, is responsible for the origins of the second law of thermodynamics. His work on the concept of entropy was later used by Rudolf Clausius and Lord Kelvin to formalize the second law of thermodynamics and define the concept of entropy. He established studies on the improvement of steam engines and groundwork for modern automobiles and jet engines. Rudolf Clausius was a German physicist, and he developed the Clausius statement, which says heat generally cannot flow spontaneously from a material at a lower temperature to a material at a higher temperature. William Thomson, also known as Lord Kelvin, formulated the Kelvin statement, which states it is impossible to convert heat completely in a cyclic process. This means that there is no way for one to convert all the energy of a system into work, without losing energy. Constantine Carathéodory was a Greek mathematician, known for his own work not based on Carnot. He states that in the neighborhood of any initial state, there are states which cannot be approached arbitrarily close through adiabatic changes of state. His work is derived mathematically and not based on Carnot's concepts of engines. First law of thermodynamics shows the relation of the internal energy of a closed system in which it follows conservation of energy. The second law of thermodynamics focuses on the flow of heat and its impacts. The heat flows from a hot region to a colder region, increasing the rate of disorder, and this phenomenon is called the entropy. Here we have a closed system with different temperatures divided by an impermeable surface. Here, the energy from the left side radiates to the right side until the system reaches thermal equilibrium. The system reaches a new internal thermodynamic equilibrium and its entropy increases. For an ideal process of heat transfer for a closed system, we have a reversible system or a quasi-static system. Its entropy is described by equation 1. This describes small changes in entropy that allows reversibility of the process. For a real system that follows the second law of thermodynamics, the entropy is shown by equation 2. The difference is that the change in entropy is greater than the heat transfer change for it to model a real system. This is an irreversible process. Heat engine converts heat into work. Heat is taken in from a source at high temperature, mechanical work is done and the heat is expelled at a lower temperature as shown in the figure. Heat engines usually operate in a cycle. They return to a point at which all thermodynamic variables are the same as they were at the initial stage. An ideal engine or perfect engine converts all the heat input to work, and this violates the second law of thermodynamics, since a real engine would always have a heat loss to the environment. Real engines convert heat into work with some heat loss. Converting all of the heat to work is impossible according to the second law of thermodynamics, and some of the heat is expelled into the environment, which acts as a cold reservoir. Shown in the figure, we see how engines lose their heat. Also we see how it is modeled, how its flow of heat moves. The work done for a real engine which has a cyclic process is given in equation 3, where the work is equal to heat from high temperature plus the heat loss. Since it is a cyclic process, its internal energy is still conserved or zero. Thermal efficiency of a heat engine is the ratio of the work produced from the heat energy input at high temperature. It is expressed by the equation 04, which we can rewrite by substituting equation 3 and we get equation 5. We can also rewrite this in terms of its temperature difference. Recall the formulation for quantity of heat and we get that the efficiency is given as a function in terms of temperature in equation 6. Here we have an example. A certain gasoline engine has an efficiency of 30%. What would the hot reservoir temperature be for a Carnot engine having that efficiency, if it operates with a cold reservoir temperature of 200 degrees Celsius? We recall the expression for efficiency for heat engines, shown here in equation 6. We rewrite this in terms of temperatures and convert the temperature to Kelvin scale. We see that the temperature of the hot reservoir is about 676 Kelvin or 403 degrees Celsius for a gasoline engine with 30% efficiency. Heat engines follow conservation energy according to the first law of thermodynamics. The second law sets the limit on how efficient a heat engine can be, which can never be 100%. Based on the conservation of energy of a heat engine, its internal energy is equal to 0. Heat engine follows a cyclic process which is due to the conservedness of its energy. Here we have a typical pressure volume diagram of a heat engine where it follows a cyclic process. Process 1 to 2, which is at constant volume, heat enters the system. Process 2 to 3, work is done by the gas adiabatically. Process 3 to 4, heat leaves the system into the environment, and process 4 to 1, work is done on the gas. An Otto cycle is an idealized thermodynamic cycle that is commonly used in automobiles. The system begins with process A to B, which is an adiabatic compression of gas and ignited at point B. Then at process B to C, heat is produced by the ignition of gasoline in an isochoric process or constant volume. After that it proceeds to process C to D, which is again an adiabatic process but for expansion of the piston engine. Then finally it goes to process D to A, where heat is released into the environment in an isochoric process. Here we have a simulated image of a piston for an Otto cycle as mentioned in the previous slides. You can see how the fuel is compressed and ignited to create the motion of motor vehicles. We see how the state changes as the piston moves along its cycle from taking on the fuel and air mixture by intake process, where the volume increases, then pressing it the next stage and pushing the piston into a cycle of continuous motion. Let us look at the isochoric processes where heat enters or QH and the heat leaves or QC. We recall that both process B to C and D to A are isochoric processes or constant volume. So the equation that describes the heat entering and leaving is given by equation 7 and equation 8. Note that the molar heat capacity is given for constant volume condition. Here we see the details of the energy process for an Otto cycle as functions for work, heat, and internal energy. We see the process start with an adiabatic compression from state A to state B. Then it is followed by the isochoric process from state B to state C. Then after that is the adiabatic expansion from point C to point D. And the final process, which is the isochoric process from state D back to state A. Here we have another type of cycle system, which is the Carnot cycle. It is an ideal reversible thermodynamic cycle and it is described as a perfect engine. The system is initiated at process A to B, where the gas expands isothermally at temperature Th, absorbing heat QH. It then proceeds to process B to C, where it expands adiabatically until its temperature drops to Tc. After that it goes to process C to D, where it compresses isothermally expelling heat Qc at temperature Tc. Finally it then goes back to process D to A, where it compresses adiabatically back to its original state. Here summarize the work, heat, and internal energy for the Carnot cycle. We see the work, heat, and internal energy equations for the different processes. The process starts with an isothermal expansion from state A to state B. Then followed by an adiabatic expansion from state B to state C. Next is an isothermal compression from state C to state D. Finally, it is followed by an adiabatic compression where it goes back from state D to state A. Here we have the comparison of the efficiencies for two different types of engine. The Carnot cycle efficiency is given by equation 6 and for the Otto cycle it is given by equation 9. Here the Otto cycle efficiency is dependent on the compression ratio of the engine. The compression ratio is the ratio of the maximum volume over the minimum volume a cycle can achieve. The ideal Otto cycle has a compression ratio of 8:1 of its maximum and minimum volume. Here we have an example on a Carnot engine. A Carnot engine has an efficiency of 30%. Its efficiency is to be increased to 50%. How much change in temperature does the source increase if the sink which serves as the cold reservoir is at 300 Kelvin? In this problem, we are asked to find the change in temperature from 30% efficiency to 50% efficiency. So to find that value we determine the difference of the temperatures at 50% and 30%. So determine the individual hot temperatures or Th. Recall the expression for the efficiency for a Carnot engine shown here. Rewriting it to solve for Th. Now for Th at 30%, its value is about 428 Kelvin and for Th at 50% we have it at 600 Kelvin. Now the difference is 171.4 Kelvin. This is the change in temperature of the source as we increase its efficiency from 30% 50%. Here we have an example of an Otto cycle problem. Let us assume an Otto cycle with a compression ratio of R equal to 9:1 ratio. The intake air is at pressure at A equal to 100 kPa or 1 bar, at a temperature A equal to 20 degrees Celsius or 293 Kelvin. Its volume at point A is equal to VA equal to 500 cm3 before the compression stroke. At this point it undergoes an isochoric process from point D, so the volume at point D is also equal to 500 cm3. This volume here is the maximum volume the system can achieve. The temperature at the end of an adiabatic expansion at point D or Td is equal to 800 Kelvin. We note that the molar heat capacity at constant air pressure is around 28.19 Joule per mole Kelvin. Its molar heat capacity at constant air volume is around 20.87 Joule per mole Kelvin. Also, the ratio of molar heat capacity is around 1.4. We identify each process first: process A to B, adiabatic compression; process B to C, isochoric process; process C to D, adiabatic expansion; and process D to A, isochoric. For letter A, we are asked to find the mass of air intake. Note that the amount of gas remains the same for an enclosed system. To determine the mass of air we use the ideal gas equation shown here. We rewrite this to solve for the molar value N. Consider a point where the variables can be supplied. Based on the given it would be at point A. Here we get that the molar value is N equal to 0.02 mole. To solve for the mass we use the molar mass equation where for air it is around 28.97 gram per mole. Multiplying this with mole value we get that the mass of air being taken in is around 5.794 times 10 to the power of negative 4 kilograms. For letter B, we are asked to find the temperature at point C or find Tc. Note that for an adiabatic process the temperature and volume ratio for 2 points is given as the equation here. We consider 2 points that have enough variables that are present, and for this case it would be points C and D, rewriting this to have an equation for temperature C. The ratio of the volume here is the compression ratio equation. We substitute the known values, we get that the temperature at point C is around 1926.6 Kelvin. At letter C, we are asked to find the pressure at point C or PC. To find the pressure at point C we use the ideal gas equation. At point C we have an ideal gas equation as shown here. The equation is incomplete and we need to find volume at point C or VC. We use the compression ratio relation. We find that the volume at point C is around 55.56 cm3. Substituting back to the modified ideal gas at point C we find that the pressure is around 5.9 times 10 to the power of 6 pascals. For letter D, we are asked to find the heat added to the system or the QH. At this process we see that it is in an isochoric process. The heat equation at constant volume is given here. Modifying this for process B to C we see that the temperature at point B is unknown. To solve this, we use the equation for temperature at an adiabatic condition, since at point B it undergoes an adiabatic condition, A to B process. Applying the compression ratio also we get that the temperature at point B is around 706 Kelvin. Substituting this value to the heat equation we find that the heat added or QH is around 510 joules. For letter E, we are asked to find the thermal efficiency. Recall for an Otto cycle the efficiency is given by the equation here. Substituting the known values we see that the thermal efficiency for an Otto cycle is around 58%. Here we have an example on an Otto cycle. An ideal Otto cycle with air as the working fluid has a compression ratio of 8. At point A has a temperature TA and mass of air equal to 1 kg. For letter A, find the pressure and temperature at the end of the heat addition process. For letter B, find the net work output, and for letter C, find the thermal efficiency. We have additional data. The properties of air at room temperature are specific heat capacity at constant pressure equal to 1.005 kJ per kilogram Kelvin. Specific heat capacity at constant volume CV equals 0.718 kJ per kilogram Kelvin. And the molar ratio is 1.4. First we identify the different processes in this cycle. Process 1 to 2 is an isentropic process or adiabatic process. The isentropic process is a thermodynamic process where the entropy of gas remains the same, which makes it reversible. The system is both adiabatic and reversible. Process 2 to 3 is an isochoric process. Process 3 to 4 is an isentropic or adiabatic process. And process 4 to 1 is an isochoric process. For letter A, find the pressure and temperature at the end of the heat addition process. The pressure and temperature here refers to the end of addition, or QH refers to point 3. So, we are asked to find P3 and T3. However, the nearest point with available given, or point 1, is 2 points away. So, we first solve some variables at a point midway between 1 and 3. Here we choose to solve point 2. Note equation for an adiabatic process, the temperature and volume ratio is given by the equation here. The volume ratio here refers to Cr. So, the temperature at point 2 is about 689 K. For the pressure at point 2 or P2 in an adiabatic process, we use the ideal gas equation. Since the number of gas, Nr, remains constant, then comparing the points 1 and 2. Equating the equations. Finally, substituting the known values and getting the pressure at point 2 is about 745 kilopascals. Now we have the temperature and pressure at point 2, which we will use to obtain the temperature and pressure at point 3. To solve for the T3, we use the heat equation where it is based on the specific heat at constant volume. Rewriting this equation and substituting the known given values, we have that the temperature at point 3 is about 1753 Kelvin. Now we have the temperature at point 3, and to solve for the pressure at point 3 we use the equation for an isochoric process. Since the number of gas, Nr, remains constant, then comparing the points 2 and 3. Equating the formula and rewriting it to solve for the pressure 3 is about 4,392 kilopascals. Letter B. Find the net work output. Recall the first law of thermodynamics. For a cyclic process we have the internal energy equal to 0. So the work is simplified as work total equal to heat total. The heat total is the difference of the heat input minus the heat output. The input and output simply refers to QH and QC. So, the net work is expressed as Q hot minus the Q cold. Here Q cold is still unknown, so we solve this first. To solve for QC we use the heat equation where it is based on the specific heat at constant volume. Rewriting this equation we see that temperature at point 4 is unknown. To solve this we use the equation here for an adiabatic condition at the process of 3 to 4. So, the temperature at point 4 is around 755 Kelvin. Substituting this and we get that the QC is about 327 kilojoule. Substituting the values of QH and QC back to the work total equation we get that the work total is about 423 kilojoule for the Otto cycle. For letter C, find the thermal efficiency E for an Otto cycle. We get that its efficiency is about 56.4%. Refrigerators are reverse heat engines where we force heat to move from a cold region to a hot region by applying work. We know that it is impossible for heat to flow naturally from cold to hot without any work done according to the second law of thermodynamics. So for refrigeration, we apply a certain amount of work to force this flow as shown by the diagram here. Heat QC is taken in from a low temperature cold reservoir and the heat QH is expelled into a high temperature hot reservoir or the environment. The performance coefficient K is given by equation 10. This can also be expressed in terms of temperature, which is the Carnot refrigerator shown in equation 11. Here we have an example of a Carnot refrigerator. A freezer has a coefficient of performance of K equal to 5. If the temperature inside the freezer is negative 20 degrees Celsius or 253 Kelvin, what is the temperature at which it rejects heat? Assume that it is an ideal system. Note that for a Carnot refrigerator its performance of coefficient is given by equation 11. Rewriting this we get an expression for TH or the temperature at the hot reservoir, and for this case it would be the environment where heat is dissipated. To find the temperature at which it rejects heat means that for a refrigerator system it is the TH. Substituting the values, we have that Th is 303.6 Kelvin, the temperature of the environment. Here we have an example for an air conditioner, which is a type of refrigerator. So we have an air conditioner that removes heat of 1.5 kilocalories per second from a large room. The power required to run it is 2 kilowatts. If the typical value of the coefficient of performance of this refrigerator K equal to heat Q over work W is equal to K equal to 1/10 of the performance coefficient for a Carnot refrigerator. The outside temperature is 313 Kelvin. What is the temperature inside the room? First we identify the given variables and convert them to the same units for quantities that are similar. So, we are given a heat that is removed in terms of heat per second, which is Q per time equal to 1.5 kilocalories per seconds. We convert this to joules per second and we have 6,279 joules per seconds. We also have the power, which is the work over time expression. We will use these values as the Q and W source and we ignore the time S since they will cancel each other out later. Recall the expression for the performance coefficient of a refrigerator equation here. We see that for this refrigerator its performance coefficient is given by the condition that it is 1/10 of the performance coefficient for a Carnot cycle. We rewrite this to solve for the temperature inside the room, which is the Tc. We get the expression here. We substitute the known values here. Note that we used the heat rate, which is in joules per seconds, and the power, which is also in joules per seconds. This is acceptable since the time parameters cancel each other out. We get that the temperature of the air-conditioned room is around 303.3 Kelvin. That is it for now, and I hope you learned something new today. For questions and comments you may send them to diyeslearningstuff@gmail.com. You may review the slide on YouTube at Dies Learning Stuff. Note, please do not forget to use your school email. Also write your complete name and class section. Thank you for listening and see you next module.